Hi, today we'll talk about livestock and climate and why we actually need a toolkit of solutions to reduce the greenhouse gases of our food system. My name is Frank Midlöhner and I'm a professor and air quality specialist here in the Department of Animal Science at UC Davis. I'm also the director of the CLEAR Center, which is a center that looks at two things. The one is research. We conduct research in the traditional way, quantifying, mitigating emissions from the livestock sector. But equally important is our communications effort. We conduct science communication with those stakeholders that are interested. Could be high school students or college students, journalists, politicians, the public at large. The CLEAR Center has really developed into a very nice center. It's only 5 years old, but it's growing and it's impactful. I'm very proud of it. We produce, on the communication side, things such as explainers that explain things that people think they know, but really don't. For example, what's soil carbon sequestration? Or how do cows affect climate? Those kind of things. And then we also write blogs, larger pieces that are oftentimes used by journalists to come up with ideas for stories they write on topics. And then we write our own news stories as well. And we have a team of communication experts that really get the information out. So research and communications go hand in hand at the CLEAR Center. Now, the topic at hand is really greenhouse gases. And greenhouse gases from animal agriculture, what we know about them, how we can mitigate those, and how we can turn something that's often viewed as a problem into part of a solution, namely by managing those gases. What you see on this slide here is the sun radiating down solar beams to the surface of the Earth. And normally that solar radiation and the heat contained therein would be reflected back into space if there weren't these so-called greenhouse gases. Gases such as CO2, carbon dioxide, methane, nitrous oxide. These gases form a blanket over our atmosphere. And just like a blanket would that you put over your body, it retains that layer, that blanket retains some of that solar heat in our atmosphere. And that's very important for life on Earth. Without that, life on Earth would be too cold. We could not really live here. We need greenhouse gases. The trouble is we have generated too many, and that means the blanket is getting too thick. And that means too much of the sun's solar radiation is retained back in our atmosphere, leading to this warming effect. So we need greenhouse gases, but not as many as humans generate through various activities. And that includes fossil fuel burning, cars, trucks, trains, planes, ships. But it also includes agriculture. And here, for example, cows, and we are talking about that today. This slide here shows all sectors of society globally and how much greenhouse gases are associated with them. And you can clearly see, while this is pretty convoluted, the most important color on this slide is really red. And red stands for all sectors that are burning fossil fuels being oil, coal, and gas. And this is the transportation sector, heavy industries, power plants, and so forth. So that's 3/4 of all greenhouse gases worldwide. And then you can also see a significant amount of green, and green stands for agriculture and forestry. With respect to animal agriculture alone, and we are talking global, animal agriculture alone generates about 12% of all global greenhouse gases. That number over the years has come down. The United Nations Food and Agriculture Organization back in 2006 thought it was 18%, 1/8. Now they're down to 12%, but it's still a sizable number. But I want to remind you, this is not a number that applies to your respective country, let's say Brazil or Germany or so, but it is a global number. In countries like the United States and most other developed countries, the contribution of livestock to total greenhouse gas emissions is generally around 4 or 5%. In many developing countries, developing and emerging countries of the world, where the livestock sector is relatively large and growing, but other sectors are relatively smaller, the relative importance of livestock can be quite high, 50% and more. So this is just to really show and make sure people understand these numbers do not apply throughout the world, but they are very situation and location dependent. So when we look at greenhouse gases, there are three in particular that are of greatest importance. The one is carbon dioxide. The other one is methane, and that's where the majority of our focus is on today. And the third one is nitrous oxide. And when these three greenhouse gases are compared to one another, the world generally uses a so-called global warming potential 100. GWP 100 was developed about 30 years ago because policymakers wanted to have an easy way of understanding the differences between things such as cars and cows and other sources of greenhouse gases. And the beauty about this GWP 100 is it's super simple. But with many things that are super simple, it is also problematic because it lacks nuance. So what GWP 100 does is it simply says that one molecule methane versus one molecule of CO2 is 28 times more powerful in trapping heat from the sun. And it says that one molecule of nitrous oxide is 265 times more powerful than one molecule of CO2. So in other words, both methane and nitrous oxide can be converted to CO2 equivalent amounts. So let's say if you run a dairy or a swine operation and it emits about 10 tons of methane, all you need to do is multiply the 10 tons you produce times the factor 28, and you arrive at 280 tons of CO2 equivalent emissions. That's what this GWP 100 tells you, okay? It pretty much says methane is a CO2 on steroids. And it would be beautiful if it were that easy, but it's not that easy because methane behaves quite differently in the atmosphere than CO2 does. And that's why there's a growing number of scientists that now has a beef with the GWP 100. Methane, in contrast to other greenhouse gases such as CO2 and nitrous oxide, is not just produced, but methane is also naturally destroyed, a process called oxidation. And that oxidation process leads to a much shorter lifespan that this gas has, meaning once a cow, let's say, belches out methane or pig's manure produces methane, that methane will linger in the atmosphere about 10 to 12 years, and then it's gone. In contrast to CO2, if we drive a car, let's say, and we burn gasoline, we produce CO2, and that CO2 will stay in the atmosphere for over 1,000 years. Similarly, nitrous oxide is also a long-lived climate pollutant that once it's emitted by a source will stay in the atmosphere for much longer than methane does. As a result, methane is considered a short-lived and CO2 and nitrous oxide long-lived climate pollutants. I really like this graph because it shows that methane needs much more nuance because methane has sources. On the left side, you see fossil fuel production and use, agriculture, biomass burning, wetlands, and so on. All of these combined, all of these sources of methane combined, produce approximately 558 teragrams of this gas. And that's a global number, 558. Let's call it 560. But in addition to sources, there are also sinks for methane. And on the right side, you see what they are. There are two sinks. The one has, as a title underneath, sink from chemical reactions in the atmosphere. And what that means is that there is a molecule in the air called a radical. To be precise, it's called a hydroxyl radical, and this hydroxyl radical destroys the methane, and that on average happens within a decade. In other words, you have many sources producing this gas, but you also have sinks destroying it. And if you want to know what the global net contributions are of all activities on this gas, then you need to subtract the sinks from the sources. Should make sense. If you do so, if you subtract the one from the other, you arrive at the number that's in the red box, and that's 10 teragrams of that gas. So this is by no means deflecting of the importance of this gas, but it's important to understand this gas is not just produced, it's also destroyed. If you now look at the two main pathways, so to say, of a fossil fuel-derived greenhouse gas versus a livestock-derived greenhouse gas, then you see the following difference. On the left side, you see that oil, coal, and gas, so-called fossil fuels, that were in the ground for a very long time, are extracted by human activity. And when we extract them, we then burn them, and we put the carbon that was in the ground for so long into the atmosphere. And that is a one-way street of carbon from the ground up into the air. So on the biogenic side, and that's the livestock side of carbon cycling, you have as a starting point CO2 in the atmosphere. Plants that the animals eat take on that CO2 and make cellulose or starch from it. But the majority of the carbon that came from the CO2 actually goes into the roots of the plants. And then sooner or later, soil microbes take that carbon and sequester it in the soil. And that's why that process is called soil carbon sequestration. Approximately a third of all human-caused carbon is sequestered by plants and then eventually going into soils where it's stored. A very important process. But of course, our animals also eat some of the above ground vegetation. And when they do, particularly when ruminants do, some of that carbon that's contained in the plant is converted by microbes in the digestive tract into methane. In the case of ruminants, that methane is belched out, and that's the main source of methane from livestock, the belched methane. And then that methane resides in the atmosphere for about a decade, after which it's destroyed and converted back to where it came from, which is CO2. So on the left side of this slide here, you see a one-way street of carbon from the ground up into the air, and it's the fossil pathway of carbon. And on the right side, you see the biogenic pathway, which is one where a constant herd of cattle or other livestock takes carbon and converts it from one form to another. While it's in the form of methane, it's a potent greenhouse gas, and because of that, we are seeking to reduce it. But the biogenic carbon cycle does not add additional carbon to the atmosphere, whereas the fossil pathway does. So on this slide here, I want to show the difference between two important greenhouse gases. The one is CO2, the other one is methane. So imagine you were to live 20 miles away from work, and every day you have to drive that distance. Let's say on Monday, you drive, you put CO2 into the atmosphere. You do the same on Tuesday, and on Wednesday, and on Thursday, and on Friday. And every time you burn that gas, you put new additional CO2 to the existing stock from the previous day, the previous week, the previous month, and so on. As a result, CO2 is called a stock gas. Okay? Every time we burn fossil fuel like oil, coal, and gas, we add new carbon to the existing stock. It accumulates. That's very important to remember, okay? It accumulates. And because of that, we see globally CO2 levels rising year by year by year. Currently, many people treat methane as if it were a stock gas as well. But is it? The answer is no, it's not. Methane is not a stock gas because methane is not just produced, but also destroyed. And that makes methane a flow gas. If you have a constant source of methane, let's say a constant herd of cattle, then an equal amount of methane that's produced by those animals is also being destroyed through oxidation. And that makes this gas a flow gas. A constant source of methane does not add additional warming. And it's not cumulative like CO2 is. And that makes a big difference as to how these two respective gases warm our planet. This graph is a little bit complicated, but I think very insightful. Imagine two sources of greenhouse gases, one being a power plant and the other one being a cattle herd. We start with a power plant that over 30 years, and you see this on the top left, over 30 years produces more and more and more power, and as a result, it puts out more and more CO2. What happens to that CO2, or what does the CO2 do to warming of our planet? You see it at the bottom. The warming of that linear increasing CO2 increases exponentially. Why exponentially? Because CO2 is cumulative, and that means every time we put this gas into the atmosphere, it's additive to the previous week, previous month, as I said before. But look what a linear increase of a methane source does. Let's say we were to have a cattle farm with 1,000 cattle, and after 30 years it's 1,500 cattle. Then that increase in cattle numbers would lead to a linear increase in the related warming, which you see at the bottom. Not an exponential increase, but a linear increase. But now comes in a more important scenario, namely one where both the power plant and the cattle herd are stable. So let's say over 30 years that power plant produces a stable amount of power and therefore a stable amount of CO2. Then what would the resulting warming look like? You see that at the bottom, the related warming would go up. Even though the CO2 concentrate or emissions are stable, the related warming of that CO2 goes up. But if we have, let's say, a constant cattle herd of 1,000 animals over 30 years, and that's the blue line on top, then you see the blue line at the bottom, the related warming will be stable, no additional warming. The cattle scenario here would be in line with what the Paris Climate Accord suggests, which is that we as humanity must not add new and additional warming to our planet beyond 1.5 to 2 degrees centigrade. So a constant cattle herd would fall into that category of not adding additional warming. But I'm not suggesting that we should stop there, that we should just hold additional warming from the cattle sector, from the livestock sector. But if we can, and we do have the ability, we should further reduce it. And then here's what happens. Again, the comparison between this power plant and the cattle herd. Let's say that power plant were to be on a trajectory to eventually be shut down because the owners of that power plant want to be net zero. Then that reduction of CO2 would lead to, and you see it at the bottom, a further increase of warming. Even though we are reducing CO2 in the right scenario, we are increasing warming all the way to the point that we shut down that power plant. And at that point, we no longer have CO2 emissions. And at that point, we from then on will have constant warming, a plateauing of the warming. So it requires us to stop the burning of fossil fuels in order to not add additional warming. That would be the scenario under the Paris Climate Accord. But see what happens if we reduce methane. And that's possible through different means. If we reduce methane from the livestock industry, then we instantaneously reduce warming. And that is a big deal. What it means is that the use of feed additives, the use of better genetics, the use of manure management approaches, all of these approaches can reduce warming and be an important part of the climate solution. So people ask me, Frank, is methane a super pollutant? And I say, well, in my opinion, CO2 is a super pollutant because even if we reduce it, the related warming still goes up. To me, methane is more of a super opportunity because if we manage it appropriately by reducing it, we reduce warming. And that really is a big deal. And because methane is the main greenhouse gas in the livestock industry, we have a special opportunity here to affect warming impacts of society. This slide here shows the estimated annual methane emissions by region throughout the world. And you can see that there are great differences across regions with respect to how much methane is produced. When I animate it so that you only see gray tones and blue, the blue is now the methane that stems from livestock agriculture alone. Okay? So that is the amount that animal agriculture puts out with respect to methane in the different regions throughout the world. If you wonder what the differences across species are, cattle versus buffalo, sheep, goats, pigs, and chicken, you see that we have a clear winner there. Cattle are the number one species with respect to methane emissions by far. So that's really what we should focus on large ruminants. Small ruminants play a role, but not a major one, and pigs and chickens are, as monogastric animals, relatively unimportant. People often ask me, well, what are the demands, the human demands for animal source foods like And here we clearly have to say, it depends. It depends in the region that we're dealing with here. You can see that between 2020 and 2050, there's a pretty steep increase projected for Asia, also for Americas, but the Americas we are talking about here is mainly Latin American countries, not North America. Europe is pretty stable. Africa is also going up, but it really is largely Asia where the growth occurs, and to some extent Africa. I get the question often, how about food choices? How about just changing what we eat in order to reduce the carbon footprint of our food system? This slide here shows data from the Our World in Data source for the United Kingdom. And you can see here that the number of meat eaters, and these are really omnivores, these are not carnivores, but people who eat meat and dairy and eggs in addition to plant-based, they're very stable. Okay? They have not really changed very much in recent years. And neither have the other ones, the flexitarians, the vegetarians, the vegans, the pescatarians, and so on. All of these dietary forms have plateaued by and large. And that is the case despite the fact that some of those particular plant-based alternatives have been promoted heavily in much of the media. But those campaigns have not really had a major impact. So while it's clear that a vegetarian or vegan diet will have a lower environmental footprint than animal source foods, it has not swayed the consumer to make large changes one way or another. What I found really interesting, and it's really something that happened relatively recently, that was the fact that the United Nations Food and Agriculture Organization, or in short FAO, put out a report called the Pathways Report. And in that report, they looked at what the steps are that the livestock industry can undertake in order to reduce its environmental footprint, particularly carbon footprint. And I find that report very insightful and want to show you one of the main findings. This slide here, this so-called waterfall figure, shows on the left side base year emissions, and that's emissions of the livestock sector as of today. And then the second column shows the additional emissions which will occur until the year 2050. And the third column then is the cumulative emissions today plus what we had until 2050 if business as usual takes place, meaning no major mitigation efforts in livestock throughout the world. So as you can see, the third column there shows the number of 9 that needs to be reduced down to 1.9. And you see that on the very right of this graph. So 9 is 9 million metric tons of CO2. E is what we would do as a business as usual until 2050. But what we really want to achieve by 2050 is 1.9. And so the FAO then said, how can we get there? How can we get to that point? And they looked at all the different means of achieving reductions. And you can see here that the FAO said the number one tool that we can use are productivity increases. Okay, that simply means we're producing more product with relatively few animals. That's the number one. The second one is breeding for low methane producing animals. The third one is improved animal health. And then come all kinds of other approaches, as you can see. So many of those approaches are approaches that are already being deployed today. I've seen all of them in developed countries, some of them in developing countries. What I also find very interesting about this graph is that one of the means that's oftentimes touted as the most important thing we can all do to reduce our carbon footprint, which is changing our diet from an omnivore diet to a plant-based diet, that dietary change has also been quantified here. And you can see it in the fourth column. And it's just simply not true that this is the main thing or a main thing of what we can do to reduce the carbon footprint of livestock and meat, but it's actually the second least effective way of reducing the impacts. And so To me, it's important that it has been quantified, and it's important that people know how much it is. And I hope that those people that are dealing with communications really use these fact-based numbers to really guide us into where reductions are possible. And that is mainly on farms and not on our plate. I want to also spend a few minutes on one of those case studies where reductions of emissions have happened and where reductions have worked out well between the public and the private sector. Here in California, we have a very strict methane law. It mandates a 40% reduction of methane to be achieved by the year 2030, so in a few years from now. So you can see on this pie graph here, dairy alone makes up a significant amount of methane emissions in California. Landfills are another source, other non-dairy livestock, a third main source. The total emission reductions, as I said, are 40%. Dairy alone needs to reduce 7.2 million metric tons. The beef sector, 1.8 million metric tons. So the question really is, can these kind of reductions be achieved? And the answer is yes, they can and they will be achieved. Two of my colleagues and I have recently written a white paper called Meeting the Call, and the URL is listed down at the bottom of this slide. We have shown in this report that stronger reductions than 7.2 are possible for our dairy sector, and they will be the result of four main approaches. The one is, due to the fact that our cows are becoming more productive, we need relatively fewer animals, and that herd size shrinkage is referred to as attrition. And attrition is responsible for a range of emission reductions that's listed here. The second most important approach, alternative manure management practices, also leads to a range of reductions. A third one, and probably the most important one, are dairy digesters. This is a facility, a manure storage facility, where you trap the gases that normally would go into the air. It's called biogas, and then you take the biogas and you convert it into utilities, into fuels or into power. And that has a very significant reduction potential, as you can see. And last but not least, there will be feed additives that we can feed to our animals in order to reduce emissions. If you add up all four approaches, attrition, alternative manure management practices, dairy digesters, and feed additives, then you will see reductions of anywhere between 7.6 to 10.6 million metric tons. Again, the goal is 7.2. We will achieve more than 7.2. And we do this because the state of California decided to use a voluntary incentive-based approach. And what that means is the farmers decide what approach to use, and they decide which route to go. The government and the taxpayers will assist this process by financially incentivizing emission reductions. Farmers will, over the next few years, not just sell meat or milk, they will also sell carbon credits. There will be market mechanisms that will help farmers do what's right, and that is minimizing emissions while doing what they're really there for, which is producing food. The dairy digesters, or covered lagoons as we call them here in California, are probably the most effective tool at this point to reduce methane emissions. You see on this slide here a pretty typical dairy. The bottom right you see a lagoon, and that lagoon is where the manure is stored. Normally it's open, but in this case it's covered. And what you see bulging out there is the biogas that I talked about earlier, 60%, 60% of which is methane. And that methane is in this case not a problem, but it's a utility. Just like the natural gas that you heat your home with or that you cook with at home, this methane is a form of energy. And we can now clean this biogas so that the methane is cleaned and then use it as a transportation fuel. Or we can burn it and make power. This technology alone, these anaerobic digesters in California's dairy industry alone have until now reduced 2.5 million metric tons of CO2e. So one technology alone has already allowed the dairy industry to achieve 30% of its methane reduction goal. And that's just the start. And it makes me really excited and bullish about this industry and knowing that it will achieve its full reduction. This is what it looks like when you take dairy renewable natural gas, that's what it's called, this biogas, and you put it into heavy-duty trucks. These heavy-duty trucks now, instead of running on diesel, do run on this much cleaner renewable natural gas, producing much fewer emissions compared to the fossil fuel original. In addition to manure technologies, there are feed additives, some of them are listed here, that will reduce enteric methane. Enteric methane being the methane that animals belch out. There are some technologies, feed additive technologies, that are bubbling to the top as being the more effective means. There are others that reduce less, and the farmers will have to decide what additive to use, if any. In addition to these additives, there will be other approaches, for example, genetic approaches, where we now have tests to find out whether a mama cow is a high or low methane producing animal, and you then only choose to breed those low methane animals, and therefore have a permanent effect for multiple generations. Other approaches are the development of vaccines. Imagine vaccinating an animal for methane, which then produces way less methane throughout its lifetime. So these are just some of the approaches that are out here. With respect to general trends that we have seen in the United States, we have already gone a long ways. For example, in 1950, we used to have a much larger herd on the dairy side than we do today. We used to have 25 million dairy cows. Today, we only have 9. But with this much smaller herd today, we have produced 60% more milk. That means the carbon footprint of a glass of milk is 2/3 smaller today than it was 70 years ago. On the beef side, we see similar developments. If you're interested in other means of reducing greenhouse gases from livestock, here are a couple of them in this Journal of Dairy Science article. They are listed as increased animal productivity, breeding, diet formulation, the use of feed additives, and so-called early stage mitigation strategies. The latter being, if you treat a calf early on in life, you might have lifelong effects on methane. Really an approach that's currently being researched, but it is being discussed in this article here. What we see as a challenge, not just as scientists, but also as taxpayers, is the fact that research funding is dwindling. What you see here is public versus private funding. You see that public funding, which is funding via governments, whether that's federal or state, is very low. And that's true for many different agricultural enterprises, but it's particularly true for animal agriculture. You see there the third horizontal column being animal systems and animal health. You see that while there is some funding, it is really small. And it is a significant challenge because the folks stepping on or stepping in are private industries, and they want to develop new technologies. And at universities, we are trying to help develop those, but that relationship is then oftentimes twisted as a bond that's too close between industry and academia. We need way more funding on the federal, on the state side, both the public as well as on the private side. Here one graph, again showing the same thing, public spending of agricultural research dollars. As you can see, it has gone down pretty drastically around 2005. A development that is really disconcerting. When we look at greenhouse gases from the animal agricultural enterprise, then it's clear that We see increases of consumption patterns in part of the world, particularly in developing countries, emerging countries. We do not see major changes in developed countries. So while Ethiopia and Sudan and Paraguay are increasing consumption, the US, most European countries are not. To reduce emissions of farms, we need a toolbox of solutions. And just like any toolbox, what that really means is that you have an assortment of different tools and you can pick which one to use to achieve the job that you seek to achieve. We do need to increase public and private research support, because in order to optimize solutions for our farming sector, we need to find out what the intended and potentially unintended consequences are of using such technologies in the real world. And that brings me to the end of my presentation. I want to thank you for your attention and invite you to come visit us in person, or maybe only virtually. If virtually, then clear.ucdavis.edu is the web address. Thanks again, all the best to you, and see you soon.